welcome to today's virtual field trip. I'm Petty Officer Patrick Enright, and I'm joined by a Navy scientist, Dr. Burton Nooner, who's here with me to talk a little bit about how light works. Dr. Nooner, how are you today?
Very good. Good to meet you, Patrick.
Good to meet you as well. So you're a scientist. What made you want to become a scientist?
Ever since I was a young kid, I was completely fascinated by space, astronomy, Albert Einstein, the theory of relativity, black holes, and neutron stars. That led me to the general
really fun stuff.
Really cool stuff. Led me to the study of physics, and now I find myself here today as a civilian scientist with the Navy.
Okay, so we're going to break it down to the basics today. We're going to talk a little bit about light, right?
Correct.
So I just got here in San Diego a couple days ago, and I noticed you got these beautiful blue skies out here, and I had a question. I was wondering, why is the sky blue? Can you explain that to me?
That's a classic question. I asked my parents that very same question, and many others like it. So let's talk about light for a moment. The reason that our sky is blue is that on a clear blue day, you have an atmosphere full of tiny particles, generally smaller than the wavelength of light. And what happens there is they scatter light in all different directions, and we know the white light of the sun, we can see it. What happens there is those particles scatter primarily the blue colors first and other colors less strongly. So when we look up at the sky on a clear day, we see that blue color. But things are very different at sunset or sunrise.
Or it's reds and oranges and
yellows. It does look different, and the reason that is true is because sunlight propagates through a lot more atmosphere. And what happens there is now most of those blue and green colors have been filtered out or scattered, and what remains is the orange and red left part of the spectrum. And that's what we see as that darker, richer color of the sunset.
That sounds pretty cool. Can we show that in the lab at all, or is there a way we can do experiments to check that, since we're here in your lab?
We are in a lab, and we can show that with a pretty simple experiment. So what I have here is a cup of standard milk that you could buy in the store, you'd find in your house.
Okay,
and I'm going to put some standard milk here. What we're going to do is put some in this large cup.
Okay.
And I'm going to add about a quart of water.
And this is just normal tap water, right?
Normal tap water, fresh water.
So this is an experiment I could do at home if I wanted to.
You could do this, yes.
Awesome.
And what we're going to see here is a very dilute concentration. So what we already see is when we take a look at it, there's white light in the room. It's very dilute.
It does look a little blue, though, right?
It does look blue, and that's what we're going for.
Okay.
Because milk is comprised primarily of very small particles similar to the atmosphere in that they are smaller than the wavelength of light. And so, again, it's scattering the blue very strongly first. And so that's what we see when we look around. The light's coming in from around the room, and we see that blue color. But, again, we can also recreate the sunset. And the way we do that is in a different setup. Now we're going to look at what light looks like through. Now this is a white lamp, but if you see right coming through this water, it now looks
a lot more orange. So it's because it's traveling much further through the water. It's scattering all the blue out of it.
All the blue is being scattered out, and what we see just like at a sunset is what's left over is mostly the orange and red colors.
That's very cool. Okay, but what about clouds? Can you explain what's going on there?
Well, you might think that they're similar, but in fact clouds and the atmosphere are quite different. Clouds are comprised of huge collections of water droplets. Those water droplets are a bit larger than the wavelength of light. So they behave differently than the atmospheric particles. Because they're larger than the wavelength of light, they scatter light also, but they don't prefer any particular color. They just scatter all the light. And so what you see then is the white light coming from the sun hits the clouds and scatters all those colors. So we see them as that bright, diffuse white color.
Interesting. Can you show us that at all?
That one is very easy to show.
Okay.
So in this case, I have the same type of milk. I just didn't dilute it at all. And as I said, milk is comprised of very small particles, but also some larger ones. But the key point that clouds and milk share in common is that they're very dense, because a cloud is very large, it's very dense. So is there's a lot of particles in here. So really what's happening is any bit of light that's hitting this milk just wants to scatter all those colors out. So it looks quite a bit different from this dilute concentration, but when they're so dense like this, you're just going to see that white appearance like a cloud.
Interesting. So because it's scattering all the colors of the rainbow, the Roy G. Biv, it's just coming out like, so all of the colors of light combine and it's just white, correct?
Correct.
Interesting. So that's visible light, but I've heard there's also invisible light. Does that get filtered by the clouds as well?
It's a key point. So we can see visible light with our eyes, the Roy G. Biv you talked about. And there are other things that we can't see. For example, infrared light, which we think of as heat in some cases, and also ultraviolet light, which many of us have learned in school, can give us a sunburn, something we don't look out for. So an interesting fact about clouds is that we now know that on a very cloudy day, you still can get about half of the ultraviolet light through the clouds down to the ground. So I learned this the hard way several years ago. You may be outside, it's a beautiful day, but it's cloudy and so it feels cooler. You might think, oh, I'm not going to get a sunburn today. That ultraviolet light can still get down to the surface, and therefore, I always want to make sure, don't forget your sunscreen and your hat, even if it's a cloudy day, because you can still get some ultraviolet exposure.
That's really good advice. So I got a question for you. All right, as you can see, I'm a sailor. Okay, I've been out on ships. I've been out in the ocean, and one of my favorite things to do is I like going out and looking out over the ocean. So that's got me thinking. How does light interact with seawater? Does that have any effect on it?
It's very important that you bring that up, because one might think, well, clouds behave a certain way because they're made of water. Maybe ocean water is the same, but it turns out that they're not. Ocean water is much more complicated because it's water with salt and a whole bunch of other organic material, plankton, other things like that. And what you may have seen in some ocean documentaries is you have clear, crystal clear blue water. Right?
Sure.
You see right through it, and it has that blue color. Also, sometimes scuba divers take pictures or videos when you're near the coast. It looks more green. You can't see as far. So there's a lot going on there. What's going on is now the combination of scattering, which we talked about, but also attenuation. And so scattering is when light is redirected somewhere else. Just like we talked about here. It hits the cloud or the milk, and it scatters back. Absorption is a little bit different. Absorption will take that light and turn it into something else, like heat or another process. So it's light that you have essentially lost from the original. And then the final concept that we have to understand is called attenuation. Attenuation simply means how much light makes it from here to there. And when you have scattering plus absorption, combine those, you get attenuation.
Interesting. So scattering is like the light hits something, and then whatever bounces off is what's scattered. And then what's absorbed is what stays in, and it becomes heat, kind of like the pavement on a hot summer day or something
Correct.
like that.
Something like that.
That's interesting, but I'd like to see if we can show that in the lab as well. Can we do that?
We can. We can definitely see that.
Cool.
So now, continuing with our theme of what we've been talking about, we have some milk, we also have some water, and one other material. So
this stuff right here.
I have in the back here a simple glass of clean, fresh water. It doesn't tend to absorb or scatter much. So we would expect it not to attenuate very much.
Okay.
The milk, as we said, is a very strong scatterer, which is why it looks white. It doesn't absorb much, so therefore most of the color comes back.
Sure.
Now, in this one, we have a new material. It's a dye or an ink. It looks very dark. It's nearly black, and the reason that is it doesn't scatter much. It's different from the milk, but it does absorb a lot.
Okay.
And what we now see with this experiment, I put light from the top. We can see that the scattering and absorbing materials look very different, but now we talk about attenuation, and that looks similar because
they both block out the light on the bottom.
Exactly, because if either scattering or absorption is strong, you're going to get a lot of attenuation. So what you'll see here, two very dark spots underneath these two materials, whereas the clean, fresh water, if you look down there, it's very clear. You can see the light coming right through it. So that shows the differences between those three parameters.
Interesting. So let's bring that back around to my question. How does that relate to the ocean and how that works?
The reason it relates very importantly to the ocean is because when you have that clear, crystal clear blue water we talked about, that type of water will not absorb much and not scatter much. It does absorb a little bit in the non-blue colors. So you can see very far, and you see a bit of a blue color. That's because the blue can propagate pretty far. But in the coastal areas where you might have a scuba diver taking pictures of fish and other material, they, in that water, will see that they can't see as far, and that's because there's now a lot more scattering happening, and the materials in the water, for example, the plankton I mentioned, they will absorb more of those blue colors. The result is a very different property, so it looks green and you can't see as far, and all of these are of interest to the Navy and also to many schools, research organizations.
Cool. So it kind of depends on what water you're in and the conditions there, sort of
Correct.
that sort of thing. That's interesting. So I'm to understand that a lot of your research here is about lasers, correct?
It also is, yes, lots of lasers.
That's super cool. So we actually had a chance to put together a package going over some of Dr. Nooner's research. Let's take a look at that right now.
When you look at a laser, you can tell right away that it's special. You might be wondering, what are some of the key differences? First, when you look at sunlight, it's broad in its spectrum. That means across the visible spectrum, it's composed of all colors, whereas a laser is more monochromatic. It's composed primarily of one color, giving it that distinct color of red, green, blue, or any other color it may have. The second key difference is that sunlight is broad in the way it lights up a room or outside. That applies to both sun and lamplight. However, the laser is what we call collimated. It's very pointed along a single direction. It doesn't spread out as it propagates very much. So you can do very interesting experiments and tests using laser light. Many of us have used lasers before. Perhaps you have a cat or a dog and you've played with a laser pointer as a toy. That's fairly safe. However, there are some bigger laser systems that may be dangerous if used improperly. The good news is that there are many best practices and safe practices that we all use daily when using such systems to keep each other safe. Now, following these practices, you can manufacture precise mechanical parts, you can treat medical conditions, you can communicate information around the globe, you can even better understand your environment. Ever since I was young, I became very interested in the Apollo space program, knowing that we could put a man on the moon. What got me interested in lasers and optics specifically was that there were some amazing experiments that the astronauts brought to the moon. One of them was what we call a retroreflector array, or a set of special mirrors that when you illuminate it with a light source, like a laser, it will come back to that original source. The reason they are put there is so that we could take lasers on Earth through a telescope and shine that light from Earth all the way to the moon. It reflects off of that special mirror, comes all the way back, and by knowing how fast the speed of light is, how fast it travels, we can calculate with good precision the distance between the Earth and the moon. I'm excited to come to work every day because I get to work on new and innovative concepts. When the sailors are out at sea, they need to be connected, and one very reliable way that they've been connected in the past has been to use radio waves. They're very reliable, they're very useful for the Navy. However, we're looking into some additional innovative ways, perhaps to get more data transfer from point A to point B, and we can do that using light. It's exciting to try these new and innovative concepts and to do new experiments in the lab, all while keeping our sailors safe.
All right, and we're back. Thank you very much, Dr. Neal. That was very fascinating. In the video, you were talking about how you can communicate using light. Is that correct? Underwater?
Yes.
Okay. What would that look like? Can we demonstrate some of that at all?
So there's such a thing as a modem. So we have radio modems. A classic radio modem is a cell phone, right? A modem is something that turns the data that we want or that we want to send into a way to make it go from point A to point B.
Okay.
And so a cell phone, as I said, uses radio waves. But there are ways to communicate in different forms. And the optical modem is one way to do that, where we have light waves. And what we have here is a set of two, very small. We have a whole system here, but it's just in the palm of your hand, these little two parts right here.
Are these lasers?
These aren't lasers. That's
Okay.
a great question.
I didn't know if I needed to be, covered
Yes.
in like a
You
suit
would,
or something.
You would need some safety gear if you were
Okay.
in a laser lab with lasers on. But what we have here are two optical modems, and each one has a flashing blue light. The blue light is an LED.
Okay.
It's very similar to what you might have in a flashlight at home. And what we can do is turn the data that we want and send it from point A to point B by the units of flashing light.
Okay. So can we try it?
Yes, we definitely
Okay.
can. So what we have here is a system where we're going to power it on, and it'll look like flashing light.
Whoa. Okay, cool.
Yes. And what we first heard, so what I first heard there was a beep. That means we're good to go. And
So we're on. We're ready
Yes,
to
we
we're
are
ready
re-
to rock.
Yes.
So what are we going to send over this?
so we're going to try sending first some music. Make sure that the link, the communication, does what we think it's going to do.
Okay.
So what I can do here is play some music.
It worked.
Yes.
Well, what if we cover up the light?
You can try it.
Can I? Well, it's not going to like burn my hand?
It's all good.
All right, so it just stopped and I'm hearing a beep.
Yes, the beep. Exactly.
Cool. Awesome.
Yes.
So this is actually transmitting the light, the music over the light, correct?
Yes, and very important though is it doesn't have to be 100%. Look, if I block it a little bit, maybe even with a screen, it'll still get through. But it is a true fact that if you fully block any signal, whether it's a radio signal or even light signal, it does have the possibility to drop out. But the cool thing is with new technology, if you only partially block it, you can still get that signal through.
That's very cool. So I'm being told I have a text message here from one of the students that's watching in. Rodette asks, Where does a rainbow come from? Can you explain that at all?
Rainbows are cool. I think most of us have seen a rainbow before, and I've, in fact, even seen a double rainbow. So,
really, what does it mean, though? Do you
well,
know?
I can tell you all about how rainbow works. So it's very interesting. People always say, I want to find the pot of gold at the end of the rainbow. But a rainbow is not something that starts at one spot and ends at another that you can go to. It is always fixed at a certain angle. So generally, a typical way that you might see a rainbow is the sun is behind you. In front of you are some clouds or some water droplets. Let's say it has just rained. And the reason that's happening is I have a graphic here.
Okay.
Primarily because the water droplets in the air, they take a spherical or round shape. And what's happening is the light rays are coming in and comprised of white light from the sun. They come straight in. And then what happens is at this first surface, they start to refract, which means bend. But if you've ever seen like a triangular prism, they bend those white light rays based on their color. So then it starts refracting. It reflects off of one surface in the back, and then refracts again, which is to bend at another the second surface.
White light out
it
with the
spreads
rainbow
it just like a prism does, and it's at about 42 degrees angle. So if the sun is behind you looking forward, you're going to see it at about a 42-degree angle. So no matter where you go, you can't ever get to the end of the rainbow, but it is a beautiful sight to see those colors of the rainbow spread out into the spectrum with your eyes.
That's really cool. So I think you've got me convinced. I want to be a scientist. What do I need to do in order to get there?
In order to get all this, it does help to go and be passionate about science and math. That's typical. But what's cool is now a lot of schools have STEM programs, science, technology, engineering, and math. Whether it's during the school day or after school, those are great programs to get involved in. And I also think, though, in my opinion, it's very important to also study very carefully reading and writing, because if you don't document really well what you've worked on, it's going to be very hard to explain to other people what you've done, and you never know. You could have the next Albert Einstein in our midst if you can explain it really well.
That's pretty cool. So we learned a lot today about how light works, visible light, things like that, and how we can transmit data over light as well. I'm told you have some people in your lab here that work on invisible light. Is that correct?
Absolutely. There's lots of people doing a variety of work here.
Excellent. So I think we have a video that goes over that. Let's take a look at that right now.
Charlie, where'd you go? Hi, I'm Dr. Brittany Lynn. I work here at Space and Naval Warfare Systems Center Pacific. I'm looking for my sailor friend Charlie, and I have a special camera to help me find him since I can't see him anywhere. I'll show you how it works in a few minutes, but I'm going to follow him right now. I can see his footprints. Oh, there he is. Oh, and he crawled under the table. Go around the table. Oh, and then they stop. Oh, Charlie, where'd you go? Oh, there he is. I can see him through this plastic that's hiding him. I see you, Charlie.
See me?
I can see you.
Hi, Dr. Lynn.
Hi. How are you doing?
I'm good. How are you?
I'm doing great.
How did you find me?
I found you with this camera. It's a special camera that lets me see things that the eyes can't see. So I can see invisible things.
Can you show me how it works, please?
Definitely, I can show you how it works. Let's go set up some experiments.
Cool.
Great. So, Charlie, we've set up some experiments in this room to help us understand how to interact with the world around us, to learn about things that we didn't already know.
Okay.
So we're going to use our senses to investigate and to learn some facts about the world. So I've filled these 2 cups with water. I'll tell you it's water inside. And I want you to tell me what's different about these 2 cups, because I can tell a difference with my camera.
So you want me to tell you what's different? They're the same cup.
Eye senses, you're using your vision to test.
They look like they're the same fill level. Different senses.
Different senses.
They smell the same. Okay. But they don't feel the same.
What's different about it?
This one's warm.
That one's warm, and that one's not
That
warm?
one's not warm.
Okay, let's take a look through the camera and see what we have. That is what this camera sees.
That's so cool.
So what we can see is that this hot cup on the right is showing us the heat of the water. That's showing up as a brighter color. It's more hot. The cup on the left is cooler, showing up as a cooler color. It's darker blue.
Are those dark spots the water drops that spilled off of my finger?
They are.
Uh-huh.
So what we have is a camera that's able to see what?
Temperature.
Temperature, a temperature camera.
Wouldn't it be cool if we could see temperature with our eyes?
Oh, that would be amazing. That'd be amazing. Then you could have seen the teapot heating up from cold water to hot water when I was preparing this experiment for you.
I would never get burned again.
You would never get burned again. You know, it was great doing experiments, but we've got to run. We've got to do some video for some students to show them what's going on in our labs. So let's go.
Can't wait.
Excellent.
Let's go.
Come on, guys.
All right, everybody, we're back, and as you can see, we've changed locations. I'm here with Dr. Brittany Lynn. How are you today?
I'm doing great. How about yourself?
Not too bad at all. So I'm told you have an experiment set up here to show us a little bit more about how light works, invisible and visible. Is that correct?
That's correct.
Cool.
Yes.
What do we got here?
Well, the video you just saw, we were talking about invisible light and how it works with different wavelengths, and that camera was different from that one. So I'm going to show you the difference between the two, and then we'll talk more about the cameras and how they work.
Okay, cool.
Okay,
all right, so what are we doing?
We're both going to be light. I'm going to be infrared light, invisible light.
Okay.
You're going to be visible light. So you're going to step on these blue lines. That's going to be your wavelength, and I'm going to step on the red lines.
I have a lot more lines than you.
A
Is
lot
that
more
okay?
lines. Yes, that's perfect. I see
All right,
that
cool.
that way.
All right, so what are we going to do?
So you're going to go the same speed I'm going. So keep your head the same as mine. You're going to take more steps than me, and let's move along.
All right, let's do
Ready?
the thing.
1, 2, 3.
Okay, I got a lot more steps to go right now. I feel like yours is a little easier.
Yes, that's definitely true. So I gave you the blue ones on purpose. so
Okay, so what did we just do there? What does that mean?
so what did you observe about our differences and what we were doing that was different from each other?
Well, I was definitely taking a lot more steps
More
there.
steps,
I'm getting my steps in for the day, so my cardio is good. I'm going to go back home and just play some Fortnite.
Excellent.
All right,
So that's
cool.
kind of indicated here by these steps here. So you were the visible light. You had to take a lot of steps to get across the room.
For sure.
I only took a few steps to get across the room. I'm the infrared or invisible light. So that means the wavelength is longer for invisible light than visible light.
Okay.
We were stepping on the tops of these wavelengths. This is how we describe light, is by this sine wave. There was something else that was different too, though. Did you notice anything else?
I mean, I feel like I'm definitely a little more worn out, you know, from taking all those steps. Is that about
Yeah, you
kinda
use
where we're
more
going?
energy. You use
Okay.
more energy, yeah.
Cool.
So the more steps you have to take, the more energy you have to use. And that's the same with the light here. Infrared light has lower energy than visible light does. So that's what describes how these cameras work that we saw before are different. If we step over here, what we have is, here's the sensor on the back of a camera. Same kind of sensor you're going to have in a cell phone, the cameras we're using right here, or the camera we saw before in the video.
Is this Charlie?
That's Charlie.
Okay.
Well, he'd be upside down in this picture, but we'll just ignore that for
Okay.
now. So every camera sensor has pixels. Now the pixels are what's different about the different cameras. In the visible camera that we have, let's say right here, what happens is we have blue energy, blue photons.
That's visible light.
That's visible
Okay.
light. And the red ones are the invisible light. And you can think of it like the blue ones go into a bucket and fill it up, but the red ones are too small. They just fall out a hole in the bottom. So we can only see the higher energy visible light photons.
Okay.
Now, if we look at a different kind of camera, like we saw in the video, what we have, we can imagine being a bucket with a small hole in the top. So it only lets in the invisible light photons, but the big, high-energy photons just kind of bounce off.
So
and they keep
because they
going.
have too much energy, they won't go in there, and the camera doesn't pick them up.
Exactly. We only see the small photons here.
Well, that's interesting. And I like your diagrams. I like your drawings. These are really cool. But we're in your lab right now, and there's a lot of exciting stuff here. So can you show us some of that stuff at all?
Definitely, definitely. And there's, another kind of light we didn't discuss out here,
Oh.
and that's ultraviolet light.
Okay.
So now ultraviolet light has an even shorter wavelength, and that makes a difference because I have lasers like that in my lab too.
Cool.
Let's go check them out. So what we'll see in here is this is a laser that's infrared laser.
This is a laser.
That's a laser. This big box is a laser.
I'm going to take your word for it.
We have another orange laser over here that's an ultraviolet laser. And then we have some lasers in the back that are big enough to fit half a classroom in.
Okay.
Those are also ultraviolet lasers. So all different kinds of systems that we use here in the lab.
So what would you use these kind of lasers for? Like, what is the application for them?
So in this space, what we generally do is look at new materials. How do we make new materials that can do things that you can't do yet for any kind of purpose? And maybe you'll even see them in your next cell phone that we're going to make. So one of the systems that we use one of these ultraviolet lasers for is this system back here.
Oh, wow. Okay, so this looks very, very technical. Can you explain kind of what I'm looking at here? Do you maintain this whole system?
I maintain this whole system, and people on my team maintain the system. So even though we may be scientists, an optical scientist or a physicist, we have to understand how to work systems like this. This is a high vacuum system. It helps us make new materials on different substrates so we can just see what they do, measure them, and see what the different parameters are. But in order to maintain these systems, I have to have a background in mechanical systems, in vacuum systems. I have to be able to do all the cables and electrical systems.
Wow.
I have to run it with the computers and make my own programs. So everything we do here is very multidisciplinary.
So did you build this yourself?
No. We
Okay.
bought this system.
Oh, okay,
yeah.
cool. But if you wanted to?
If I
You
wanted
could.
to, yeah, we could. We
Excellent.
definitely could.
I'm seeing a lot of interesting stuff on here that's not, it doesn't seem like, lasers to me. Like there's a bike chain, there's aluminum foil. What's going on with that?
Yeah, great eyes. So some of the stuff we use in labs is very similar to what you might find at home. This actually came from my home. This is just aluminum foil. It's helping
Okay.
us shield the system
This
right
isn't
here.
like space aluminum foil.
No. This is just like regular aluminum foil.
Like I can
yeah.
make a baked potato.
You can make a baked potato with
Okay,
this,
cool.
definitely. So we use, regular life kind of things to do really cool science with. Up here, the bike chain you pointed out, that helps us move things inside up and down.
Mm-hmm.
That's the exact same thing as a bike chain. We even have gears and sprockets in there, and all of these systems, if you reorganize this, maybe you could ride it around like a bicycle.
Okay, that's cool. So what happens in here? Is this like a big chamber? What would you use this particular piece of equipment for?
Yeah, so we shoot lasers in here, and they hit different materials and explode them onto other materials.
That sounds really exciting. Is there a big bang, or is it just
Not
like
in this system. It's
Okay.
not a big bang. It's under a vacuum, and so you're not going to hear anything because sound requires, different. It requires a medium to propagate through, like air.
Interesting.
But if you were to look in here, you'd see a plasma forming. And so what we do in this group is a lot of work with plasmas. We do more plasma work in the room next door. We can go check it out if you'd like.
Real quick though, what is a plasma? Can you describe what that is? Is that just like a ball of goo, or what is a plasma?
No. A plasma is something that is the way we describe the state of the matter. And so it's just a collection of excited electrons and neutral media. So if you just take electrons, like your chemistry class, and you start stripping them off of molecules, and they're all in one place, we call that a plasma. And
Okay.
so we'll see more about that in the next room.
Cool. So what you said is that you know about all these other systems, but particularly you're an optical scientist, correct?
I am.
So what does that mean? Like can you tell me about your background and and what you went to school for?
Yeah, so I went to the University of Arizona at the College of Optical Sciences for an undergraduate and a PhD, both in optical sciences. So what I learned about was telecommunications, exactly what Dr. Nooner just showed you, where you have information travel through light in the internet, through your cell phones, all these kinds of things. Displays, like on your cell phone. Cameras, like on your cell phone. Cell phones really embody a lot of things that we do in optical sciences. But just like this, it's a combination of physics and math and engineering and all sorts of fields that you have to pull together something where you can really start making a difference.
Excellent. Well, you said you have another lab over here
I
with
do.
even more exciting stuff.
Even more exciting stuff.
Let's go check that out.
Let's check it out.
So what are we doing in here? You said this was plasma in here?
Yeah, we make plasma in here to do all sorts of different measurements and studies with. What we're going to start with is showing how we use plasmas with this system over here.
This is cool. What's going on here?
Yeah, so we have lasers. Those big boxes there are laser systems.
Okay.
And then we have optical components. We'll maybe get into that in a little bit. I can show you what they all do. And what we do with that is we make plasma in air or on materials in order to make them into kind of a speaker. So when you have a plasma, you have a lot of like charges. They don't like to be together, and so they want to expand very quickly. That expansion happens at faster than the speed of sound. You might have heard of Mach 1, Mach 2, or something like that. So they
And
expand
that's the speed of sound and
3
multiplied.
times the speed of sound. So if something's traveling that fast, you get a supersonic shock wave that starts to travel, and that becomes very loud.
Apparently we have a video of some of these experiments going on. Let's go ahead and take a look at that video real quick. Okay, so that was really cool. What I really like is you looked like you just suspended a ball of light in air, and that was the plasma, right?
That was the plasma.
And so what was the sound that I was hearing?
So that sound is that expansion, that supersonic shock expansion. So for the video, I think they had to make it much quieter so it wouldn't, blow out the eardrums of everybody in there. But that expansion is what makes the sound. And so what we're doing is these lasers have a certain rate that they fire at, and so every time that fires, we get a shock. And so you can hear that with your ears, just like a speaker does.
Interesting. So you can, in theory, you can make a speaker so I can play music over the light.
Exactly, exactly. Or communicate with someone else. So a lot of what we do here is based on communication. We want to help people talk to other people wherever they are.
Interesting. So I'm seeing a lot of really cool doohickeys and doodads over here. I don't want to touch any of them. Can you explain to me what some of those are?
Definitely I can. So over here I have some other examples.
Oh, okay, cool.
Okay. So what we have here, this is a lens.
Okay.
We use this, and you can touch it, just don't touch the shiny surfaces.
I'll do my best.
So we use those to focus the light. So we'll take a big beam of light and we'll focus it in to make a sharp point. For
Okay.
our system, that's where we make a plasma.
So this is what you have a whole big bucket of light. You just want to put it all in one spot.
All into one spot.
Okay, cool. What does
Now,
this one do?
That's a wedge. That is something that has a flat surface on one side and a wedge surface on the other side. And so what we can do is pick off little bits of light to do some kind of analysis on the laser beam while we're doing experiments.
That's really cool. Okay, so what else do we have?
So this is a mirror. This is not like the mirror you have at home, though. The mirror you have at home is for visible wavelengths of light. You can see yourself. It looks kind of like aluminum. This is a dielectric mirror. So if you can see at home there, what we have is a mirror that may look green or purple or blue to you, depending on the angle. But it perfectly reflects the infrared. So to the infrared, it looks just like the mirror at home.
So even though I can see through it, it looks like a window to me because it's invisible light that will be able to bounce off?
Exactly,
Okay.
exactly. Now this is how we stop the laser beams. So once we're done with them, we don't want them just shooting around the room anymore. We use special things. They're called beam blocks that collect the light and then dispose of it safely.
Interesting. So what is inside this that
Inside
blocks
this
the light?
is graphene. So it's just like a really, really thick layer or graphite of black that perfectly absorbs the light.
Does this get really, really hot when you shoot a laser into it, or how does that work?
Yeah, our lasers, it does get hot. You might see signs all over the labs here that say caution. We usually have things that are a little bit dangerous in here, and so we have to use a lot of safety features.
Interesting. So what is this crystal-looking thing that I have right here?
This is a beam splitter, and so what you might be able to see at home is that it's damaged. That was because our lasers are very high energy.
It looks like it got a little charred there in the middle.
Yeah, and so what happened is the laser beam hit the middle, and then it just exploded the glue that sits in the middle. And so sometimes with these high power lasers, some of the lower power equipment just doesn't work very well.
So it looks like when I'm looking at this, like it's bending the light. Is that correct? Is that's what it's supposed to do?
Exactly. It reflects some of the light and then transmits some of the light. So we kind of use it to either combine two beams or we can split one beam into two beams.
Interesting. So it seems like all of this is sort of either to manipulate the light or stop the light or change it in some sort of way, right? That's cool. And what is this camera-looking thing right here?
This is somewhat similar to the camera that we had in the VAST video, except for this one looks at infrared
Smaller,
light that's
for sure.
definitely smaller. It doesn't quite see the thermal infrared. That's a much longer wavelength.
It's not on. Wait. Here we go.
This is down in
Everything is green now.
Yeah, everything's green. That's a fluorescent imager. And so it takes wavelengths that go from visible up through kind of near infrared, and it makes them visible so your eye can see that whole spectrum.
So what are some of the other kind of like real world things that you would use lasers for, like out there in the wild?
In the wild. But real world, so you have laser pointers at home. Those are kind of things you might use in your daily life. You might see lasers in like laser rangers. So we have them in the military as well, but even at home, if you have something that's a range finder, that's a laser inside. It's a very short pulse laser, shoots out, comes back, and it measures the time it took for that pulse to get from one place to the other, because light always travels at the same speed.
So obviously the lasers that you can have at home and play with your cat, those are for the most part safe, but some of these seem a little dangerous. What do you guys do to stay safe here?
Yeah, we're definitely focused on safety here. We have to always make sure we protect our eyes. Those are very important parts of your body and very sensitive.
Sure.
And so what we have, these are goggles. They're a little bit different
Can I put
than
them
some.
on?
Go for it.
Oh,
we can
I'm
both
so
put them on.
excited.
So these goggles look a lot like swim goggles. Because
Everything's
we
green.
want to protect everything around. Yep. And the fact that they're green means that everything else is being blocked. We're only getting green light through the goggles.
Cool.
So everything else is going to get blocked. Now, I wear these goggles when I work in here. I also wear ear protection because, like you saw in the video, that noise was in the video.
It was really
That's
loud.
really loud in the lab. So we wear these earmuffs to help protect our hearing because you don't want to lose your hearing.
What?
You don't want to lose your hearing.
I'm going to take these off.
Yeah, these aren't great for conversations.
Yeah,
for
not
sure.
so much,
Yeah.
but definitely blocked out a lot.
It
All right.
did.
What are some of the other ones here? These are different colors,
These
right?
are different colors.
Those
So
are
these,
stylish.
yeah, these are stylish. Go for it. These are for different wavelengths of lasers. So just like the wavelengths and the cameras
I
make
think
a
these
difference.
are out of regs. I'm not supposed to wear these in uniform.
Yeah,
Pretty
these
sure.
block different colors. So these are past orange, those past pink. Those are more for infrared colors.
Cool.
And we have lots of safety features.
That's exciting. So I have another question here from some of the students that are watching. This is from Madison. And Madison asks, is ultraviolet light considered an invisible light?
Well, definitely it is. So I have a picture here that we use in the lab that shows the different kinds of light that you have. So the visible light is this spectrum here. It goes
That's
from blue
almost
to
none of
red.
it.
Almost none of it. All
Wow.
of this is light. This is higher energy. That's higher wavelength. The visible spectrum is just this little piece right here. Now, the infrared, which we were just talking about and we saw some scenes of, that's this section up here. The ultraviolet UV is down here. It has a higher energy and a smaller wavelength.
But what's really cool is once you go even higher energy and shorter wavelengths, you get X-rays, just like at the doctor's office.
Okay, so then
those
you
are
can see
light
people's
sources.
bones.
Exactly, you can see through your body. They're so high in energy.
And then this stuff over here makes you into a superhero, correct?
Yeah,
That's how that works?
The gamma rays. Up here you have actually the radio waves that you can listen to. Microwave, we don't want to play in there. That's like the microwave that's in your house. Radio waves are the ones that you can listen to in your car radio. And then long radio waves, those travel a really long distance.
Excellent. So even though these are just regular radio waves that we're listening to on our devices and things like that, that's still some sort of light.
That's still light. It's still an electromagnetic wave.
Interesting. Well, that's very cool. I think we're wrapping up. We're about all the time we have right now. Thank you guys so much. Dr. Lynn, thank you very much for joining me.
Thank you.
I want to thank Dr. Nooner as well as SpayWar for having us out here and showing us this today. I want everybody to join us for the next virtual field trip we have on behalf of Defense Media Activity and SpayWar and the United States Navy. Thanks, everybody, for joining us. We got to wave. Goodbye. Bye, everybody.
Bye.